start with a little story. I'm old, so this goes back 20 years. It was the winter in Boston, 1981. The snow was a meter high. I was feeling really fed up, and I just came across a little note. That was at MIT in Boston. And I came across a little note. Eric Drexler, telephone contact to California, the MIT Nanotech Club. I thought, oh, that'd be interesting, so I went along there. And it was Eric Drexler, one of the fathers of nanotech. He gave his talk, and then it was question time, and I started and said, Eric, how about a Femtotech? And I was really surprised by his answer. He poo-pooed the idea. He thought it was ridiculous. So I said, well, wait a minute, aren't you doing just the same thing that your critics have been saying about you and your ideas on nanotech? But he didn't buy it. Anyway, so on and off I've been thinking about the possibility of a Femtotech. It wasn't until I eventually retired and really started thinking hard about it, having enough time to study enough particle physics to be able to do it. So I've made some progress that you'll see today. So think about it. Femto, that means 10 to the minus 15, so 1,000 for the trillionth of a meter. So if a femtometer technology could be made, it would outperform nanotech, which is 10 to the minus 9 of a meter. It's 1,000,000 times smaller. So the density of your components would be 1,000,000 times 1,000,000 times 1,000,000. So the density goes up by a factor of 1,000,000 cubed. Okay? And each little component is 1,000,000 times closer together, so the signaling speed between them would be 1,000,000 times faster. So you got 1,000,000 cubed times more components per unit volume, and the signaling speed of each one, the operating speed of each one, is 1,000,000 times faster. So the total performance of that femto gadget would outperform nanotech by a factor of 1,000,000 to the power 4. That's a trillion. Okay? Now in this talk, I'll also give you a little attotech. Atto, A-T-T-O. That's 1,000 times smaller than femto. And right now my pet project is I'm thinking about string tech. Okay. Go right down to the smallest measurement scale that humanity's even thought of, and that's the so-called Planck scale. And that's 10 to the minus 35 of a meter. So, and that really got me thinking, if our future massively intelligent machines are smart enough to be able to implement these technologies, then a so-called femtolect, that's a femtometer scale artilect, it's artificial intellect, would outperform a nanolect, that's a nanoscale artifact, by a factor of trillion. So you can see there would be pressure after a while to just scale down and down, because the smaller the faster. Okay? So you can just do more. So that really got me thinking, well, you know, our universe is, what I was saying earlier today, 7.7 billion years old, our solar system is 4.6 billion years old. There's a trillion stars out there. And a similar number are second or third generation stars. Also the physics is the same everywhere. So you've probably heard of Fermi's question. Fermi said, well, if these highly intelligent creatures are commonplace in the universe, and there was this famous question, where are they? Why do we have no? Why isn't there sort of like McDonald's in the sky? Why isn't there obvious evidence of massive engineering projects that are obvious? We just sort of look up and see them. We don't see them. And I think, and this is the hypothesis, I think the answer is that in a sense, massive, hypermassive intelligence is potentially everywhere. But it's so tiny, you can't see it. So if you have a technology based on quarks and electrons, and they're the two basic ingredients of everything, all substance, well, unless you start counting dark matter and dark energy, the stuff we know about, they're effectively point particles. Right? They have no size, unless you go to string theory, but then you have to go right down to Planck. So the potential of putting these components together is just astronomical, which again reinforces my thinking that the potential of these massively intelligent machines is far greater than the conventional thinking at nanoscale. But even nanoscale would outperform what our brains do by a factor of a trillion. So what I'm saying is this enormous scope. Okay, so I'll give you some a taste of how at least computing at the femto level might be done. So Nanotech's well funded. So what's next? Well, it can't be picotech. That's 1,000 times smaller than nano, because there's just nothing there. Nature does not provide anything at that scale. Okay? Like the atom's what, 10 to the minus 10 of a meter? So what's smaller than an atom? Well, the nucleus. That's 100,000 times small. So that's 10 to the minus 15. So you go from you have to go from nano to femto. And the nucleus is about 10 to the minus 15, so the protons, neutrons inside the nucleus are more or less the same scale. And inside the nucleons, protons, neutrons, are 3 quarks. So if you're going to start thinking about a possible femtotech, at least computing, you need to know the properties of the quarks and gluons. What's a gluon? A gluon is sort of like a photon, but it binds, just from the name, in a sense glues, bonds the quarks together to make a proton or a neutron. Now to study all that, if you like math and physics, because it's not easy, there's a specialist branch of physics called QCD, Quantum Chromodynamics. And that C, the chromo, might give you some clues. Stands for color. And what's color? Well, it's a kind of charge. And the quarks have ordinary charge that you're used to, electronic, positive and negative charge. But they have another kind of charge, which comes in 3 kinds. That's why it's called color. But it has nothing to do, remember this, has nothing to do with the ordinary color that we're used to at our scale. I mean, they're just labels. I mean, you call them blim, blam, and bloom, or ABC, or XYZ. 3 labels, like just red, blue, and green. So it comes in 3 kinds of colors. Well, actually 6, because there's also anti-red, and anti-green, and anti-blue. Now, the quarks have these 3 different colors. You have a red quark, a blue quark, a green quark. Remember, it's not real colors, they're just labels, they're just abstract properties. And the gluons that bind the quarks, they are bicolored. They have two colors each. So, for example, you can have a red and an anti-blue, or you can have a blue and an anti-red. And remember that, because that become critical for computing. I'll use those gluons to change the colors on the quarks, and hence the computing. Okay, so set that, correct. Now, these colors, red, blue, green, when you have an interaction, those colors are conserved. You sum them all up, and what you start with is what you get towards the end. So have a look at the bottom here. Is here you have an interaction. So you get a red quark, it emits a gluon. So Q for quark and G for gluon. Yeah. Now have a look. You see on the left-hand side you've got a red, so you've got a charge, color charge red, and on the right-hand side you've got a blue and a red and an anti-blue. Now the X and the anti-X cancel, right? So the blue and anti-blue cancel, so you're left with a red. So you have red on the left side, red on the right side. So color charge is conserved and it's kept, it's constant. Right? And if it doesn't happen, that interaction is not possible from without. Okay? Now a quark can not only emit a gluon, but also absorb one. So in the middle of the screen you've got an example here of an absorption of a gluon by a red quark. So you see there the anti-red and the red, they cancel, and all you're left is blue. So what you've got there is, by absorbing a quark, a gluon, the quark changes its color. Now, for those of you, the computer guys amongst you, you're beginning to sense the possibility you might be able to compute with these kinds of phenomena. Right, so how to do that? What are the basic ideas? Well, let's use the red quark and the blue quark, the colors, to represent bits. Okay, so we'll just make a definition. A red quark, by definition, is a 1, as in binary digit bits. And a blue quark, blue is 0. Okay, so if you want to change a 1 to a 0, well, you change the red quark to a blue quark. If you want to change a 0 to a 1, well, you change the blue quark to a red quark. Okay, just basic bits. So how do you do that? Well, if you have a computer science background, you'll know that these 3 logic gates, in combination, you can do anything with them. You can compute. You can build a computer with these 3 logic gates, even less if you keep it simple. So the so-called OR gate, AND gate, and NOT gate. So NOT, you just, if you have a 1 in, the NOT gate will switch it to a 0. 0 goes in, will switch it to a 1. An OR gate, if just one of your inputs is a 1, the output is 1. And for an AND gate, you have to have input A and input B to be a 1. Both of them have to be a 1 for the output to be a 1. All other cases, 0. So if I can map phenomena that's going on at the quark level, quark and gluons, if I can map that into these 3 logic gates, it's big if, there's lots of engineering type problems, but in principle, if I can do that, then I can compute at the femto scale. So you could have femto computers. So you could have artificial minds at the femto scale and at the atom scale. And hopefully maybe in the conference 6 months from now, I'll be giving a talk on Planck tech. Planck creatures, mind boggles. Okay. Okay, so with those 3 gates, you can compute anything, right? Computationally universal. Right. Now, before I get into the nitty-gritty, I'm not doing the time.
Seems like 5 more minutes.
Okay. So, how do you implement an OR gate? Sorry, NOT gate. Well, have a little chamber, a little volume, and you send in from the left-hand side a red quark here, and inside this chamber, this little volume, tiny, it might be the size of a proton or something, but that kind of volume, put red and blue gluons. Well, specifically red anti-blue or blue anti-red. So if a red one comes in, it gets changed to a blue. Okay? The gluons change the color of the quark. And if a blue goes in, the gluons change it to a red. So that's a NOT gate. Okay? Now, given the time, I'll just give a few examples. I won't have enough time. Now, to implement an OR gate, remember, if one of them is a 1, the output is a 1. So you have these 2 chambers with 2 little volumes. On the left-hand side here, if a red quark comes in, then a gluon is generated. It's created. Red anti-blue gluon is generated, which enters then the second chamber, second little volume, and as well as the second bit that comes in. Well, say they're both red, so the first bit and second bit are red. So when the first bit goes in, that generates the gluon, which goes into the second chamber, and a second red quark goes in, and the gluon has no effect on it, because otherwise charge is not conserved. So the second red gluon just goes straight through. So the outcome is a red gluon. Okay? So 2 reds in, you get a red out. Now second case, you've got a red in and then a blue quark goes in. Now the gluon that comes out of the first one, that will change the color of the second red into a blue, change the blue into a red. So you've got a red going in and a red will come out. So red, blue, or 1, 0 gives you red, which is 1. So 1, 0 gives you 1. The third one, just quickly. So now you've got a blue and a blue and a red, sorry. Now if a blue goes in, the first one, nothing comes out. No gluon comes out. And you've got a red going into the second one, and no gluons there, so the red will just go through unchanged. So you still get a red coming out. Okay? So 0, 1 gives you 1. Now, when they're all blues, no gluon comes out from the first one. The second one goes in, there's no gluons to change it, so it just goes through unchanged, so it comes out blue. So 0, 0, 0 gives you 0. Okay? So you've got the OR gate, implemented in quarks and gluons. Now, I don't have the time to give you all the and, but it's a bit more complicated. There are like 3 chambers used, and then these PowerPoints, will they be on the website? Will all the PowerPoints? If you want to study it, you can.
Yeah, sure.
Also, it's an essay. It's an essay in Humanity Plus essays. If you want to go into the details. Now, there's also Attotech, so we can go down another factor of 1,000 times smaller. And instead of using gluons, you're using the weak force particles. Remember, there are 4 forces in nature: strong nuclear, electromagnetic, weak nuclear, and gravitational. So if you use the weak particle forces, W plus and W minus, you're not changing the color of the gluon, you're changing its flavor. In other words, its type. Now, there's 6 types of quarks. There's up, down, strange, charmed, and top and bottom. There's 6 types of quarks come out of this famous standard model. Now, the weak particles can change the flavor. They can change the type. So you can change like an up quark into a down quark, or a down quark into an up quark, and then the same logic goes through. Right? Just all those chains I was talking about. You're doing just the same thing. It's the same logic, but it's 1,000 times smaller. So you have the basis of an attotech. This is all with known physics, right? 10 to the minus 18 of a meter. Okay, now I'll skip ahead a bit, get to the philosophy. So, yeah, with all these techs, microtech, nanotech, there can't be a picotech, but femtotech, attotech,
Zeptotech.
Zeptotech.
Yoctotech.
Yoctotech. Planktech, right? Under 10 minus 35. So that has implications, right? So I think I see here an answer, and one of them, to Fermi's famous question. Like if you start, it's like a real paradigm shifting in your thinking, the way of looking at the world. If, it's a big if, but if massive intelligence is everywhere, like why are all the electrons the same? As though they all came out of the same production line. Why is that? Could it be because they're manufactured? Like if you start seeing intelligence in the elementary particles, it makes you sort of more inclined to deism, isn't it? Instead of just being dumb, inert, useless gizmos, there may be whole civilizations at X-tech scale inside elementary particles. So instead of looking for SETI, search for extraterrestrial intelligence out there, how about looking for SIPI, search for infra-particle intelligence, right here inside? Because that's maybe where the real intelligence